Hello everyone, welcome to part 2 of lecture 5. So in this lecture, we're going to touch upon the infinite limits and limits at infinity. So now first, let's look at the infinite limits. So when we talk about limits, it's actually referring to the value of y or f of x, right? So itself, the value will approach infinity. Now, this includes the positive infinity or negative infinity. So when we write the infinity, it could be positive infinity or it could be negative infinity. But sometimes we also write use this to denote the positive infinity. So it depends on the context. In any case, so now let's look at one example. Now, suppose we have this function, and if we plot the graph of this function, it's looking like this. So we have this line segment and this line segment, right? We know that obviously these two lines are separated by this vertical line here. So this vertical line is called the vertical asymptote, right? So in other words, the idea of infinite limits, or in other words, we talk about the limit that is infinite, is referring to the vertical asymptote, right? So it's interesting the value of x such that, right? So as a shorthand, such that y is infinite, right? Could be positive, could be negative. All right, so in this case, based on this graph, we have this vertical line here, which represents the infinite limit of this function. There are several meanings. So first one, the limit itself does not exist. So if we look at the graph on the top right, so this graph here, as x approach the value of 1, so this is 1, right? So we're approaching value of 1, and the value of y is only to become bigger and bigger, right? However, if x approach 1 from the left, right, so it's becoming smaller and smaller. So in other words, if we express it mathematically, so we have this one. So so if x approaches 1 from the right, the value is going to be approaching positive infinity, and then it's approaching from the left, right? And then it's going to be negative infinity, which means that the limit itself does not exist, right? So it's same meaning, and what we call from based on this is that the vertical asymptote is at the place where x equals to 1. Right, so this is about the positive, the infinite limit, and based on analysis, the function itself, we know that the domain itself is actually not equal to 1, right? And the vertical asymptote is at 1, and based on this, we can tell something that the vertical asymptote appears when the value of the denominator, right, is 0. And this is sort of our indicator to tell that well, the potential vertical asymptote could exist, right? So let's look at some general results. First one, a polynomial has no vertical asymptotes, right? A polynomial function, it could be a line of any degree of flexibility, and it's basically there's no vertical asymptote because it's continuous across the whole domain, right? Sorry, because it's continuous across the whole domain, right? Second point, a vertical asymptote of a rational function can only occur at the zero value of its denominator. So we look at what happens if the denominator becomes 0, and it give us the potential candidates for the vertical asymptotes, right? So let's look at a few definitions. So first definition is talking about the infinite limits and vertical asymptote. So we see that this vertical line, so x equals to a, so it's a vertical line. It's a vertical asymptote for this graph if one of this happens. So if f value goes to positive infinity, if x approaches to the approaches A from the right, or goes to a negative infinity, and it happens also x approaches A from the left. So it could be any case, right? So if x approaches A from the right, then f could go to positive infinity or negative infinity. And this also applies to the case when x goes to A from the right, right? So in either case, if x approaches a value, right, could be approach from the left, from the right, and if x goes to infinity, then we call this vertical asymptotes, right? So this is how we define vertical asymptotes and also the infinite limit. So that's one theorem to help us to locate the vertical asymptote of rational functions. So we have this form here, which is the numerator function, a polynomial function, and the denominator, another polynomial function. So if we have this case where the denominator function is 0 at a particular value c, right? And also the numerator function is not 0, then that's an obvious sign that we can say the x equals to c is our vertical asymptotes for this graph. Right, so this basically gives us a tool to tell for a rational function how to find the vertical asymptotes. Right, so what happens if both are 0? Right, so n of c is 0, d of c is 0, then we know that this is going to be an indeterminate form, right? Which is like this. So this can be an indeterminate form, and this rule, this theorem does not apply. So what do we do now in this case? Again, so based on last lecture, we're going to apply the algebraic simplification, so that we cancel out potential common factors and then calculate the limit. Right. So this is so when we deal with rational functions, then we know how to proceed. So start from the denominator, and then say what happens to the numerator. Right. So if it's not 0, then we apply the theorem. If it's 0, then we perform the simplification. Right. So so this part is just to illustrate further what do we mean by x x of equals to a is a vertical asymptote. So it could be x approaches a from the right, and then from the right it can be positive infinity, negative infinity, or if we approach from the left, right, positive infinity, negative infinity. So as long as that's one value, such as the value is of f is infinity, then we can say it's a vertical asymptote, right? So let's look at one example. So in this example, we have this form, and of course, our usual procedure is to look at the denominator to say what happens if it's equal to 0. So x squared minus 1 equals to x plus 1, and x minus 1, right? So we can say that there are two cases when when the denominator equals 0. So it could be x equals to -1 or x equals to 1. Right, so there are these two cases. Let's say this is case 1, this is case 2. So for the case 1, right? So what if x equals to -1? And let's denote this is n of x, this is d over x, just to make it easier to analyze. So if x equals to -1, so we have, of course, we have nx equals to 0, and we have so dx equals to 0, nx equals to we just plug in, right? And we can see that it's gonna be so cancel out -2, right? So this matches our previous theorem, which say that if the denominator function is 0, the numerator function is not 0, then we can apply the theorem, which is that the vertical asymptote is gonna be at the particular value of x equals to -1. So this is where we have a vertical asymptote. Right. So this is for case 1. what about case 2? Let's still evaluate what happens to the different parts of the quotient. So d of x equals to 0, n of x in this case. So 1 plus 1 minus 2 is also becomes 0. So now this becomes the usual indeterminate form, right? So in this case, what do? We perform the simplification, right? So now f of x becomes, we're going to take the limit, of course. So x is still approaching the value of 1, right? And we're going to see what happens. And we just perform the algebraic simplification. So in this case, the numerator function becomes x minus 1, x plus 2. So we can do a verification, can expand it out, x squared plus x2 minus x minus 2, right? So this cancels out, then this gives us x squared plus x minus 2, right? So most of the time we can just try it out, say if this matches the original results, and then the numerator will have x plus 1, x minus 1. So in this case, because it is indeterminate form, can match this out, and then this becomes x plus 2, x plus 1, and of course, naturally, this becomes 3 over 2, right? So in this case, the limit exists when x approaches 1, and the value is 3 over 2, right? So this is how we would approach analyzing the vertical asymptote of a function. Okay, so now let's move on. Let's look at the limits at infinity. So this actually analyzes the vertical asymptote. So at infinity, meaning what is the limit of y, right, or f of x, when x goes to infinity, right? It could be positive infinity or negative infinity. So both applies, right? So now let's look at a few cases in terms of domain and for different functions. For example, as we know for this case, the value of x squared. Now the domain is all real numbers, right? So this can be any place in the real line. And what if x goes to positive negative infinity or positive infinity? Both gonna be infinity. So the limit itself is infinity, right? Or we say that the limit does not exist when x goes to infinity, right? For the square root of x, we know that x cannot be negative, so positive or equal to 0. And when x goes to infinity, this also goes to infinity, right? Same for the log function, the logarithm function, a natural logarithm of x. Right? So x needs to be positive, and then when x goes to infinity, this results of the function itself is also goes to infinity. Right? So this is just to analyze a few cases of the functions we know already. And then some general results. So for p, if there's a positive p, then this value, when we are given a function, itself is actually approaching infinity, right? So this the function itself is going to infinity, and if we take the inverse of this function, then it's becoming 0. So that's actually quite what we use to analyze the limit of a function later through some examples. All right. So p could be any positive number. P could be 2, could be 3, could be any power function in this case, as long as it's positive. So symbolically, we can represent it this way. So if x either approaches positive infinity or negative infinity, and we say that it's actually a horizontal asymptote. In this case, it's a horizontal asymptote. If any of this happens, then we say y is equal to b, right? So it needs to be both cities. So this is all here. So as long as one side satisfies the horizontal asymptote condition. Okay, so now let's look at just one example. Let me see what else. Okay, so yeah, this just to illustrate, we have actually two cases. X could be positive infinity or negative infinity, and yeah, and also a function may cross a horizontal asymptote. So if say we actually, okay, so if we're looking at this function, and what happens if x goes to positive infinity, right? And we know that as x goes to positive infinity, this curve will approach the horizontal asymptote of y equals to 0, right? And that's the case. However, we could have some another function to say this is also this approaching 0, right? But this comes down, something like this. So in this case, there's a point where the function courses y equals to 0. So this may course, because functions could be a different form. And in this case, we're only seeing that x approaches positive infinity, to be specific. Then y goes to, well, y will be 0, which is our horizontal asymptote, right? Okay, so now let's look at a few case studies. First one, this is what we analyzed earlier. So if x for a positive number p and k, which is any real number except 0, then we have that if x goes to negative infinity, so this will become a very big number, right? It could be very positive, could be negative. When we take the inverse, it's going to be very small, so it's going to be approaching 0. And this the same argument applies for this case, right? So if we multiply k, then it's going to be becoming very positive or negative. And same for this case, when s goes to the infinity. So because k could be positive or negative in this case, right? So let's see how this rule is applied when to help us analyze the horizontal asymptote. So here we have the function here, which is looking like this. We're asked to analyze the limits of this function as x approaches positive infinity and negative infinity. So in this case, what we can do is to express it as differently, right? So let's look at the case when we have limits of p of x when x goes to infinity, right? So we need to apply some transformation here. So we just write x equals to positive infinity, and because this is the so-called leading term, right? This is a leading term of a polynomial function, which is p of x. Now I want to transform it to something like this, right? So because now this becomes 0, we can cancel it out. So how do we do? We can just extract the leading term, right? 2x cubed. Now we have 1 minus, so it's going to be 1 over 2x minus 7 over 2x squared plus 3 over 2x cubed, right? So this is how we would transform it, so that now this looks much more familiar, right? So we have these two portions here, and it's of course easier to analyze. So we have these two parts, and this is multiplication. So let's be more specific. We can apply the limits to the first part times, right, the second part, which is like this. Just write it down. Oops, this is let me erase it. Okay, this is minus plus 3 over 2x cubed. Okay, now let's look at the second part because it's easier to handle. Well, what if x goes to infinity, right? So as x goes to infinity, then this become 0, right? This can cancel out. This also becomes 0. This will become 0 based on the rules we have here. So the whole term is going to be 1. Now let's what we are left with is just this term here, right? So this is the only term, and if x goes to infinity, then this would also be infinity as well. And if x goes to negative infinity, then this also goes to negative infinity, right? So now things becomes much easier to analyze just after doing some transformation, right? So let's move on. Okay, so for the limits of polynomial functions at infinity, right? So what we want to look at is that for a function of this form, which looks just like the polynomial function we talked about earlier, right? We have a bunch of coefficients, so-called coefficients, that's associated with each so each element, right? Different elements has different degree of polynomial. So this is nth degree, which is x to the power of n. This is n minus 1's degree, right? So this is 0th degree. This is first degree, right? And we call this our leading term, right? So when we analyze what happens if x goes to the infinity, like what's the case? Now, we need to remember that this term, the leading term, is actually has the sort of the biggest power because it grows the fastest. Now, in the extreme case, when we look at a bunch of elements, and we usually tend to only look at the element that grows the fastest, which is this one, right? So that's why we can say the limit of the whole function is actually equal to the limit of this term because it sort of dominates over the other terms of the other elements, right? So this is because itself is x to the nth power, then it could be cos positive infinity or negative infinity, right? Okay, so that's also the same for the negative infinity case. Okay, so now let's just look at one example. Suppose we have the function here, then I want to transform it to something else, right? So we can apply the same trick by extracting it out, right? So I'm just writing it in one shot because this is what we'll do if we were to write it separately. So 5 over 3x plus 3 over x squared. This is 1 plus 7 over 2x squared, right? So if we multiply inside, then we get the same form. Now this is two parts. So the limit when x goes to infinity, this function would be taking the limit of both sides, right? So 3x squared to x squared. Actually, we can already cancel it out. Sorry, it's a multiply of another portion. So I just okay, let me just write it down. 5, 3x. And as I write this down, it's actually very easy to see that this portion is becoming 1 as well. So this could become 0 because x squared goes to infinity, including x squared. This becomes 0 as well. This also becomes 0 because this x goes to infinity, right? So this whole term is actually becoming 1, right? So now we're only left with this term. What this term gives us is just 3 over 2. Right, so we can see that the limit of this function is 3 over 2. So this is the horizontal asymptote when x goes to infinity, right? Okay, so let's look at the second case of rational function. So the rational function itself is works similarly. So we have the definition of the rational function here. We just take the leading term, right? Because these are terms that dominate. Now, what we need to sort of consider at this stage is that we need to compare the value of m and n, right? So because they are both the leading terms, we need to see which one is bigger, right? So there are three cases, of course. First one, what if n is the bigger one? So we have the denominator, which is the dominating case, right? The dominating term. So if that's a case, then actually the denominator grows faster than the numerator. So that makes, of course, the fx goes to 0 because the denominator grows faster, right? And then this line is our horizontal asymptote. on the other hand, when both are equal to each other, then we can just cancel them out. So this is our the horizontal asymptotes, or y equals to this one. So just the division of these coefficients, right? And then the third case, what if the numerator is the dominating term? Then it's actually the numerator grows faster than the denominator. So we actually have the value will become positive infinity or negative infinity, right? So in this case, it will not have a horizontal asymptote because it's also growing, right? It's an infinite case. Okay, so that's that's for the rational function. And then now let's look at three cases, and these three cases actually both of which actually you can work it out very fast. So without even using the technique, which is just expanded out. So you can see that's okay for the first one. We can just say we know already the leading terms. We can just say this is gonna be limit of x goes to infinity, 5x cubed over 4x cubed. It's gonna be 5 over 4, right? So a very straightforward. So for the second case, let's extract just the leading term. Right, so it's gonna be, remember to write this portion because we are still applying the condition that what happens if x goes to infinity. Right, so this is gonna be 3 x to the 4th power and to the 6th power. And then let's simplify a bit. Right, so this is still 3 over 8 x squared. We just cancel out the common portion, and as s goes to infinity, this becomes 0, right? So this will become 0. So for the third case, now we have here 2x fifth squared and 6x cubed. Just simplify a bit. So this is x squared over 3. Right, so what happens now when x goes to infinity? This will become actually infinity, so the limit does not exist, or the horizontal asymptote does not exist. Right, so that's just for the rational functions. Okay, so that's it for this lecture, and thanks for watching. I hope to see you in the next lecture.